Hi folks, today we're going to revisit some differentiation techniques. So let's start off with a nice easy one to differentiate. So obviously this is a super rough function for us to differentiate with standard techniques. We've got a product on top with a quotient. There's a chain in this, there's a chain in this. There's two layers of chain in this because there's an outermost squared and then there's a cosine and then there's a 3x inside. This is going to be just horrible. So the thing that is going to make this easier is using logarithms. Now you might look at this and say there are no logs in it, but we can do anything to an equation as long as we do the same thing to both sides. So we're going to use logarithms basically for the reason that they were invented. They were invented by John Napier to make multiplication easier, turned multiplication into addition, to make division easier, turned division into subtraction, and to deal with powers in a more easy fashion. So let's recall our log laws. I wrote them for natural logarithms, but they work for any log base. And none of this has anything to do with calculus. These are all properties of logarithms. Ln AB turns into ln A plus ln B. Ln A over B turns into ln A minus ln B. And you can pop a power down front. So how that's going to help us over here is if we take the log of both sides. So I'm going to say ln y is ln of this whole mess. Once I've taken the log, I can start to use log properties. So the one that jumps out at me is that there's division here. So maybe I'll rewrite this as ln of that whole top, which was 3x minus 1 all cubed, times root tan x. And then that's going to be minus the ln of cos squared of 3x. Now just to be clear, cos squared of 3x means cos x all to the power of 2. So I've used a log property. But that's not the only log property I can use. I could also look at the multiplication here. That looks a lot like this first log law. So I can rewrite 3x minus 1 all cubed plus ln of root tan x. And square root of tan x is a tan x to the power of a half. And minus ln of cos of 3x all squared. And it doesn't matter what kind of brackets you use, whether they're square or they're round. So I've split it up with log laws. I've done no calculus stuff yet. I can use some more log laws. I can pop all those powers down front. So I get ln y equals 3 ln of 3x minus 1 plus a half ln of tan x minus 2 ln of cos 3x. That may not look simpler than the original definition over here, but the ln of y is split up into a bunch of different components. And all of those components on their own are really easy to differentiate because we have a song for it. Original on the bottom, and then its derivative on the top. So, simplify. Let's actually differentiate now. So to start with, we'll differentiate this ln y, and we'll just use the sum. So we'll go original on the bottom, and its derivative, which would be y prime, on the top. Then I have 3 ln of 3x minus 1, so that 3 stays, it's a coefficient. And I go original on the bottom, and its derivative on the top. Half stays. Original, when we have ln tan x, so tan x goes on the bottom. Derivative on the top. Derivative of tan x is secant squared x. And finally, we have a minus 2 ln of cos 3x. Now be careful here. Original on the bottom. Derivative of cos 3x is going to have a little chain in it. Cosine goes to negative sine. Nothing happens to the inside. Then times the derivative of the inside, which would be 3. So I'm going to put that over here. Now we can try and isolate y prime, which is what we're trying to find. So y prime, let's just times both sides by y. And then simplify these. So 3 times 3 is 9. Okay, what do we get here? Secant squared x over 2 tan x. And over here we're going to have negative 2 times negative 3 is positive 6. And this is sine over cosine, so that's just tan 3x. Okay, that is an okay version of the derivative of this whole thing, but it's written in terms of y. There's one last little substitution we can make. Since we've got a y here, we can just replace it with the original question. Y is 3x minus 1 all cubed times root tan x over cos squared 3x. Once we replace that y with this whole mess, and we keep all this stuff, because that was part of our differentiation process, we've got a correct derivative for the original question. Now, when would we use this technique? We'd use it when things are rough. I think it would be fair to say that without this technique, this derivative would take us all day, and we'd make a bajillion mistakes along the way. What we get out of that last question is that difficult products, quotients, and other functions can be simplified using this technique of logarithmic differentiation. That means inserting logs where there were no logs to begin with. We'll go through a set of steps on how to do that, but I think it's worth mentioning at this point that we've just come out of optimization and related rates, and for each of those I've recommended a 5-step process, and sometimes those steps get all jumbled up. So I think in the end what we want is enough fluency or automaticity with any general technique that it becomes ingrained in us, that we're not thinking, okay, which 5-step technique for this one? So that all your problem-solving stuff, once you have enough fluency, turns into this. This is the generalized thing we're aiming for. Generalized problem-solving strategy. Number 1, do things that make the question easier or possible or just more familiar. Repeat that as needed, and then solve. Once you have enough fluency with a problem type, they'll all feel like this. We're probably not there yet with this technique, so let's check out the steps that I'm recommending. So number 1, when you have these rough functions, take the natural log of each side. You can do anything to a function as long as you do the same thing to both sides. Simplify with log laws. So you do as much splitting up as you can with log laws, and then you differentiate each side. And if I had to say a common mistake that I'll see, it's that people will do step 1 and then step 3 and then try and come back for step 2. That would be like trying to make chocolate chip cookies by putting in the chocolate chips after you've baked the cookies. It doesn't work. The order of the steps matters. Natural logs of each side, simplify with log laws, differentiate. When you do that, the left side is going to be y prime over y, because it'll be original on the bottom, derivative on the top. You'll isolate y prime, and then finally you'll just rewrite in terms of x, because your answer will have a y in it until you sub back in from the original equation. So having those steps in front of us, let's try another one. In this question, we have 2 clues as to why we should use logarithmic differentiation. Number 1, it says use logs to differentiate. Number 2, it's a mess. So let's follow our steps here. First step is just take the natural log of each side. There we go. Some people will just write ln in front of the question itself. Next step, use log laws until you can't use log laws no more. So the first thing I notice here is that there's some multiplication. Let me deal with that. Great, so I used the log law of addition over here, split it apart a bit. Some people are going to do a bunch of log laws in one step. I'm just going to do one at a time. The next thing that jumps out at me is that there's division, so I'm going to use this log law. I also may rewrite this as a power of a third. So you can see this term here turned into ln 5x minus 3 minus ln of x squared plus 1. You might be tempted to differentiate now, and you could, but it would be better to make your life easier first. Finding the derivative for the top of this whole thing is going to be a pain. So we can use this log law of powers. And it is not differentiation, it's just a log law. I pulled that power down front. Now I've used all the log laws I can. I can't pull this 2 down front because it doesn't apply to the whole thing that's being logged, the whole binomial here. So this is as far as we can go with log laws. Now we're ready to differentiate. And to differentiate, we'll just sing our way through it. Ln y becomes original on the bottom, derivative on the top. This is 1/3, it stays, and then original on the bottom, and its derivative on the top. So sine 3x is going to turn into cos 3x. It has a little chain, though, that the log laws don't break. So sine 3x, sine turns into cosine. The derivative of 3x is 3 from the chain rule. There we go. All right, next one. Original on the bottom, derivative on the top. And lastly, original on the bottom, derivative on the top. Great. At this point, we can try and get y prime on its own. So that just means timesing both sides by y. As I do that, I may do a little cleaning up here. 1/3 times 3, those are gone. Cosine over sine is the cotangent. So we have cotangent of 3x plus 5 over 5x minus 3 minus 2x over x squared plus 1. The actual differentiation was pretty easy. The only problem with our answer is that it still involves a y. So let's make that substitution. Where we have y, we can replace it with the definition of y so that all of our answers in terms of x. So I'll have y prime equals, I'll try and sneak this in here, the cube root of sine 3x times 5x minus 3 all over x squared plus 1 times cotangent 3x plus 5 over 5x minus 3 minus 2x over x squared plus 1. And done. If you did this just using product and quotient rules, you might get a different looking version of the same answer. It might have a common denominator, but this is definitely going to be an easier way to get there. Here's an elegant little function, especially if we consider it for positive x values. And it points to the fact that logarithmic differentiation is not only good for messes, it's good for some weird stuff. So I don't know exactly how to deal with this. We can do it without logarithmic differentiation. Maybe I'll tack that onto the end, but it's really slick with logs. So step 1, take the log of each side. Step 2, use log laws. So that x can come down front. X ln x. All right, at this point, there are no more log laws we can use, so we're going to differentiate. One thing to notice, though, when we differentiate is that this is a product. So in that product, we would have a first term, and hopefully at this point you're just thinking derivative of the first times the second plus first times derivative of the second. But if we're still thinking in terms of u's and v's, u is x here, u prime is 1, v is ln x, v prime is 1 over x, and then we'll just differentiate. So the left side will be original on the bottom, derivative on the top, so that would give us y prime over y. Over here, we're going to use our product rule. So u prime v, 1 times ln x plus u times v prime. So x times 1 over x. Any of the differentiation of logarithms were contained in the product rule there. So let's see what we've got next. That would give us, I'm just going to rewrite again. Just to clear up any confusion, I might put this term first. So x times 1 over x is just 1. 1 times ln x is ln x. And I write it in that term just to be clear that the only thing that's being logged is that x. Okay, checking our steps. We have log both sides, we've used log laws, we've differentiated. Ooh, now we've got to isolate y prime. So that means times it by y, and we get by 1 plus ln x. And lastly, we're just going to sub in for y. Instead of y, we'll write x to the x. So that gives us y prime is x to the x 1 plus ln x. Okay. Or if you write it in Leibniz notation, that would be dy by dx is x to the x 1 plus ln x. Logarithmic differentiation is a technique that you can use in a lot of different situations. But when a function is simple, you probably don't need it. When it's either weird or a mess, like the first two we did today, that's when logarithmic differentiation can really save you a lot of trouble. So those are the big ideas for today. It's distilled down into these 5 steps, which hopefully eventually becomes these 2 steps. Do stuff that helps, and then solve. I'm going to do this in a different way, just to pad out the end of the video, but this really marks the end of the instruction. So good luck with the practice questions, and let me know if you do have questions. Okay, here we go. An alternate, and I would say less slick approach, would be to recall this property, a equals e to the ln a. Basically, these are opposite operations, so they undo each other. That means you could rewrite x as e to the ln x. So let's do that over here. I'm going to replace this x right here with e to the ln x. It's all to the x. Great. We can use our exponent properties that say powers to powers. You multiply those powers. That should be not that bad to differentiate. So when we differentiate this, there are no logs, so we just have y prime equals. And the rule is with an exponential, you do nothing. And then you have to multiply by the derivative of the inner part. So that was the inner, is x ln x. It's a product, so its derivative of its first part would be u prime, its derivative of its second part would be 1 over x. And so the inner prime is going to be u prime, which is 1, ln x, which is v, plus u v prime. Okay. In other words, if I switch these around, I'll have 1 plus ln x. That's the derivative of the inner, and that's what we need to times by from the chain rule right here. We need inner prime. So we'd have 1 plus ln x. At the very end, we can say, oh, e to the x ln x. We actually already knew that that is x to the x, because all these steps mean y. So we have x to the x, 1 plus ln x. I guess it is still pretty slick, but it requires you to have a good understanding of your logarithm properties. Either way is fine. You're only really responsible for one, and I would be inclined to use logarithmic differentiation. Okay, I hope that was exciting. If you have another way to do this question, let me know in the comments.